Do you know what nanotokens on Solana are? Neither do I, but let's find out together. Hello and welcome to another Solana tutorial. Today we're gonna talk about nanotokens. Not sure if that's the actual official name for that, but there's a new token standard I've heard. At least somebody developed something that's supposedly more efficient than the token programs. And I want to have a look at that because the token programs are the most important, or let's say the most used programs on Solana, if we accept the native programs like the system program. But yeah, token programs make up, I think I read, about 8% of Solana's CU, because tokens have so many use cases. And the current implementation of the token programs is what it is and might be able to be optimized. Of course, that comes with other trade-offs, but I do want to have a look at those and see if nanotokens would be a good alternative to the regular token programs. So let's dive in and have a look at Cavemanloverboy's nanotokens. This guy does so many things. Nanotoken. Yeah, there you go. That's the repo. There's no official docs on that or anything. It's just a repo by Cavemanloverboy. And it's the second time I use one of his repo for one of my videos. So this guy, shout out to this guy. Right, so Nanotoken is a zero copy, non-alloc token program for Solana. Highly optimized for transfers. Okay, so they optimize for transfers, which is what the token programs are mostly used for, to transfer tokens. Yes, you also use them to create tokens and burn tokens and set authorities and whatnot, but the main use case is still transfers, and the instruction that is mostly called is the transfer instruction. So that's the one that they try to optimize here. They also support batch invocations, allowing multiple instructions to be executed within a single program invocation. So multiple transfers, I assume. Because with every instruction that you call on a program, it requires CU, and what they try to optimize is the CU usage. If it were to be used, it could reduce the token program block space on mainnet from 8 to 10% to 1 to 3%, which is quite some significant change here. Block space. And that is measured in compute units. So we try to reduce the compute units required by the transfer instructions. Okay, what else is in those docs? Partial equals can be reduced via memcopy syscall. Do I need to understand this? Something more efficient, I guess. This is interesting. Instead of a pub key, they use a 8-byte mint index counter to distinguish between mints. So in other words, mints are sequentially labeled with numbers. Kind of reminds me of the, what was it called? Inscriptions. Fun fact, I didn't like that. Do I like this? I'm not sure. It saves us a few extra compute units because we check a number instead of a pub key. Yeah, that makes sense. Creating a token account for a particular mint doesn't require passing in and validating a mint account. You just need to check if the mint is smaller than the current mint index, which means you just check if the mint is a valid mint. You're not checking that it's the specific mint, which I guess is good enough. On the contrary though, yeah, since we have this config now, we need a write lock on that config because there needs to be one account that stores the current mint index. So what is the highest number of the mint? Because, you know, sequentially we're numbering them. And that then also requires the write lock when we create a new mint. They're making the assumption that mints are not created often enough, so that doesn't bother us, which, okay, could be true. Definitely compared to, you know, transfers, creating mints is not as frequently used. And also creating a token account on a particular mint requires the read lock on the program config as opposed to read lock on the mint account. And mint accounts there is more, but it looks like we don't have mint accounts anymore. We just have token accounts. Actually, wait, no, do we have mint accounts? Probably still need mint accounts to, you know, define decimals and whatever. And then he writes, I think this was a mistake. It becomes a little difficult to batch create mint and create token account since the mint index is not known in advance. Yep, that makes sense. Yeah, two possible fixes. So yeah, I mean, that's what we see here. This is basically just an experiment where they try out different things to make it more efficient, and turns out maybe that's not the right way to go. But you gotta try in order to figure it out, right? Presently, a user can only have one token account, and tokens account cannot have the authority transferred. That's also interesting. So it's a immutable owner per default and only one token account. However, people request that non-canonical token accounts should be permitted. They might have use cases for it. Probably there are ways around it with, other wallets. But yeah, this lean implementation just allows every one user to have one token account, which is the default behavior, or what should be the default behavior. But with a token program, you can create as many token accounts as you want. And that has advantages as well. But maybe for efficiency reasons, or just because he thought it would be more safe, they did it this way. I don't know what hammer is. This thing. Probably a CLI initialize hammer. Performs the hammer operation. Is hammer send several? We'll see. So that seems to be the CLI to use it. And that's most likely the actual program. Declare ID. Gigabit. Do you think that's deployed somewhere? Not under this address on mainnet, and it is under this address on devnet. Upgrade authority, twist. So they seem to have deployed this program for testing purposes. I'm assuming that it's that. It is certainly a program account. So that means maybe I don't need to deploy it myself, which would be great. Kind of want to look at one of those transactions that I didn't send myself. We have account. That seems to be a transfer. 48 compute units. What? Wow. 1, 0. Transferring 0 tokens. Is that what you're doing? They're all transactions in the same blocks. Somebody was doing a lot here. Okay. Here we have some state stuff. Program config. The program config literally just holds the mint index. So the program config, that one global account, just holds the mint index 8 plus size of self. So we have a discriminator probably as well. Discriminator and config bytes. The account discriminator. Okay, so that's, this part. Here's the config. So 0 is uninitialized. 1 is for a config. It can be a mint account, it can be a token account, and it can be a vault info, whatever that is. So yeah, those are the two that we know. Config is new because we have this global config for this program. But yeah, nothing special here. A mint looks like this. It has the mint index. So that's not a pub key, that's this unsigned 8-byte number. And then the authority, I guess that's the mint authority and or freeze authority. If you can even freeze those tokens, not sure. Since it's lean, probably it's just the mint authority. And they say all zeros is used as none. So it's not an option, that authority. We don't have 4 additional bytes for if the authority is present or not. If the authority is not present, we just write zeros there. That makes sense. Supply and decimals as we are used from the regular account. And then we have 7 bytes of padding to have a multiple of 8, which also makes sense. Because there's this single byte. Why not? Also here, the space has the discriminator and the size of the mint. Makes sense. Owner check. If mint.owner is not program, invalid account owner. Yeah. Discriminator check. If it's not the mint, discriminator invalid. Yeah, also makes sense. Good. And then we have a token account. The token account has the owner, the mint, and the balance. Also nothing new except the mint. We don't provide the actual mint account. We just provide the mint index, which is a bit weird actually, because with that index I can't get to the decimals directly. I would need to first find the right account, although maybe those accounts are then PDAs and they're deterministically derived, so from the mint I could get directly to the mint account as well. Not sure, but let's see this. So the token account is derived with the owner and the mint and that program ID. Let's see, is the mint also derived? No, doesn't look like the mint is also derived. So that looks like it can be any account. Yeah, apparently. Okay, and then the vault. The vault has a oh, That's for changing between Tokenkeg and this native one. So we create the mapping with the Tokenkeg mint, the Tokenkeg vault, and the Nanotoken mint. So I assume it's something like we give you a mint from the old token program or the regular token program and a vault. So that's probably an address that this program controls. And then you can deposit tokens into this vault and mint yourself the equivalent nanotokens. And then the other way around as well is what I assume just by reading, this. The vault is derived from the Tokenkeg mint. So every Tokenkeg mint has one vault. Okay, and that's it. That's the lib. When we process the instruction, check the config, Solana program, program memory, sol mem copy. That's what they were talking about. That's more efficient than pub key equals. If the mem copy isn't 0, if there is something that was copied. It's an efficient way, I guess. It's nice, actually. What is this config account, though? Maybe I should load the... Wait, I'm gonna clone this whole repo. We're gonna look at it in here. Makes it probably nicer to look at. So, consts. The config account. It just has a constant pub key. Sure. And that I can actually look at. Except it doesn't exist. That's not good, because that will mean that it's not working. But this one does exist, right? The program is deployed. Or at least something is at that address. Who knows? Okay, anyway, so they check the program account. Fine. Check the system program. Again, same thing, system program. And they're doing it like this because this is more efficient than a pub key compare. Then they pass instructions. Instructions in instruction iterator. Because we can have several instructions in one actual instruction. And then they get the accounts for that index. Interesting. This is actually a nice implementation. I'm not sure if it's nice, but it is something. I understand what's happening. So what instructions can we do? Initialize config, initialize mint, initialize account, initialize vault. So all of the initialize the accounts. And then we can mint, we can burn, we can transfer. And we can transmute, which is probably the thing with, either from Tokenkeg to Nano or the other way around. But that's the thing that I'm not so interested in. I'm mainly interested in the actual transfers. And before we can do that, the actual inits. So let's see if we can get that to work, huh? Because I mean that lib.rs is pretty well written. I know what it is. It has the state stuff in the same file, which I would put in a separate file, but that's about it that I can complain here. It has all the instructions and all the instructions are then in here. Cool. This is just entry point stuff that I don't think I need to understand. So they seem to be reading the accounts directly or something like that. I don't know why they do that. Probably to be more efficient. Whatever. And there we have some SPL stuff, but that's probably just relevant for the vault. Just gonna ignore this. Okay, and let's have a look at the actual instructions. Maybe init config. Somebody gotta do that once, I guess. Check the initialize config. That's the one and only time any account data is mutably borrowed in this instruction. Yeah, and all that's happening here is they set the mint index to 0. Cool. Which it should per default anyway, if you just create that account. But also you need to write the discriminator there. If it wasn't uninitialized, we throw an error and we write the discriminator to the account discriminator config. So that's where the 1 is written to into that account. But that's it. That's all the init config does, as you would expect. And then an init mint takes the authority and decimals, then checks the program config, checks if that account is uninitialized, then writes the mint discriminator as with the previous instruction as well. And then we write all that mint stuff. So the mint index is this mint index, which we have from the config probably. Yeah, the index here from config account mint index, which we also increase by 1 afterwards. Then the authority is the mint authority that comes from the arguments, I guess. Yup. And supply is 0, max decimals is 12, and the mint decimals also come from the arguments in this function and really come from the arguments here, which really the arguments here, which somehow should come from the data. Where does that happen? It comes from the instruction directly. And the instruction comes from the instruction iterator, which comes from the data. Yeah, right, because we can have several instructions within the same Solana instruction, Solana program instruction. So in here we can actually have several. Right. Okay, that makes sense. Okay, I really hope I managed to call this. It can't be so difficult. I'm just spending 1 hour to read the program, then I understand it, and then I can call it, right? That's how it works. So yeah, that was the create the mint, like initialize the mint. Probably not more in there then, right? We write this, that's okay. And then when we need to actually first mint some tokens. We provide the mint account and the to account, which is, I guess, self-explanatory enough. And then a transfer, that's the actually interesting stuff. Transfer arguments is just the amount. We expect those keys. We return early if we transfer 0. Maybe that's why we got such low compute units on that one. Because if we transfer 0, then we don't need to do all the other checks. Check that the owner signed. That is important, yes. And only then we load the accounts. Yeah, all unsafe stuff. I don't know what that actually does, but I'm assuming they do it that way because it's more efficient, reading the account directly. Check the disk. No one else should have view on this account's data. Right? They make the assumption that they're the only one reading this, or something like that. I don't know. Then we check the balance. If we have fewer tokens than what we want to transfer, then obviously that should not work. Check if the owner is correct. Again, with this mem copy, we check that the from owner is the actual owner. So the token account owner is the owner who is the signer. Then if the token accounts have different mints, that should also not work. And if all those checks went through, then we do the transfer, which is basically subtract them from here, add them to here. And we can safely subtract because we did do the check here that we don't go negative. The only thing that I still think could be a bit unsafe is this part, because that can be an overflow. Wait, actually, can it be? No, because that would mean that the total supply of tokens would need to be more than the max that those numbers support. Because I can't have more tokens total than the total supply, so that's why this is also safe. Okay, no, this is also safe. Yeah, because we saw that check here. No, it was in the mint. That's why we saw it. There. Mint account, supply, checked add. If we can add that to the supply of the mint account, then it's fine. Then we add it to the token balance as well. But otherwise, the total supply would exceed the maximum. That's what this checked add checks. So then we're safe that we also in the transfer will never overflow those values. Okay, good. Yeah, I mean, nice implementation. Can I make it work and test it and see if it's actually so much more efficient than the regular token program? That's the mission now. That's my challenge. And if nothing else, we learn how we read Solana programs here. Or at least you see how I do it. I go through the source code. Now I have an overview of what that should do. It's actually not a complicated program. It's relatively simple. And now we just need to figure out how to call it. We do have the source code, so we should need the IDL, right? An IDL would, in that case, actually be helpful though, because otherwise we need to deconstruct the source code, which just means mental work. But it's okay. We can, however, also have a look at this hammer, because I think that's what's used to actually call that program. But on the other hand, that also seems kind of boring. But that's cool though. You can do it all in one instruction. You call the Nanotoken, and the instruction data is just all of this. First we do an initialize account, then we do initialize account arguments, then another initialize account. So there we say do this instruction, then we give the instruction data for this instruction. So we basically build that ourselves, that one instruction actually has several instructions. We should have different names. But yeah, so basically here we say we do an initialize account, and that's what the initialize account takes as instruction data. But it's all actually in the same instruction, just sequentially. And then we add another mint, and then the mint args. That's how many we want to mint. I just sent this transaction. Maybe I do want to get this to work just for fun. And then hammer, hammer seems to be a test where we send transactions per second and for a certain time. Which kind of transactions? Initialize account, mint sum, where's the actual, here's the send loop. The send loop probably do some transfers. Yeah, there, instruction data, number of transfers, 2 transfers, a transfer, and the transfer args, discriminator offset, amount, and the amount is 1. So yeah, you need to write that super complicatedly to get that data in there. But yeah, that's how it works. Because it's not the same offset. It's, because there's several transfer instructions in the same instruction. And yeah, you just always transfer 1 token. And then we extend token account, signer, token account, signer. So apparently every 2 transactions we send it from the one to the other one, so we send it back and forth. Interesting. Yeah, do some compute budget, and then we build the actual instruction with all the sub instructions, and we sign it and send it. Cool. Yeah, a little bit of spaghetti code, but whatever, it's readable. And that's probably a single transfer. Yep, looks like it. Cost, what is that? Solana cost model, calculate cost. But that probably doesn't send it, but just simulates the cost or something. I don't know. Cool. I mean, while we have the CLI, such that I don't need to build it myself, even though I kind of like the challenge of building it myself, but would be a waste of time if we have a working solution here. So let's see if we can run this. Let's see if that program is actually deployed and we can use it. So does that initialize the actual program as well? Yeah, program config. The initialize does initialize the program config. That's interesting, because the program config can also be like any account, right? Here, do they use program config? What's that account? Where does it get it from? Create account. So they literally create that account in a separate transaction instead of putting it in the same transaction. But fair enough. But yeah, they create an account. But I don't think that we need to have it at this location. Also, that is dependent on the payer. So every payer will have a separate config then. I think this is more of a proof of concept than an actual we want to use this productively, so we just use it as it is. But point is, we create our own program config as well, it seems like. Okay, we need a key pair. Nanvo, almost nano. I'll take this one. Get myself some sol. And then we compile this. Hammer time. 1.18.1. Required by package Solana program runtime. So we have versions here, but okay, maybe I increase those versions. Okay, then I also need to change it in Nanotoken. This is gonna break stuff, I'm pretty sure. Here I have the equals. That's where my issue is. Let's just try. There we go. Much better. Dependencies, my favorite topic. I just assume that the new versions do the same, right? No! What's going on? Linking failed. In function entry point. First defined here. Multiple definitions of entry point. First defined here. Right, you can't have 2 functions called entry point. Do I even need that? Like, why do I? Let's pretend we don't. Well, just the program ID. I'll give you that. More spaghetti code. No op ID. There. Have it. Have it. Have it. Cannot call non-const in constants. Let's not make it a constant. Just want you to compile. That's all. I don't mind if I need to do it ugly. There's also probably a better way to get rid of this double entry point thing, but I don't know how. So I'm doing it the best I can. It's always so fun if stuff suddenly works. Okay, actually maybe in release. Build it one more time in release. Yeah, why not? Do we have a target now? We have the hammer. Here we go. So now we have a target, release, hammer. Hammer time. Wonderful. So initialize. Not present. What? What's not present? Program or what? What are we complaining about? Oh, hold on. RPC endpoint. Maybe we should start here. Give me those. We're gonna go to DevNet. Try that again. Oh, now I need to build it again. Damn it. Okay. But I still get not present. Not present my ass. What's not present? All of those things? Yeah, probably. Hold on. Config JSON. Payer JSON. Oh yeah, all of those things are not present. That's true. So where is that path? It looks like we don't even get here. Maybe that environment variable is not set. Actually, can I do something like this equals dot and then this stuff? No such file or directory. Okay, that's better. Path is nothing. Getting there. But then let's... No, I'm gonna hardcode this. Whatever. Actually, I'm gonna make my workspace keys. I have the payer. What else do we need? The config. Oh, there we go. And the config. Create me a config. Config. A mint. And a chat1 and a chat2. 1, 2. Okay, let's see if I can load those key pairs. There we go, loaded key pairs. Wonderful. Create account and then we fail. Why do we fail? Invalid program argument. Transaction pre-flight failure. Invalid argument. Program invoke. Config does not have expected pub key. Haha. Because shit. Oh no. Oh no. Oh no. Okay, shit. Still, that's bad. Because it turns out that yes, the way this is deployed, hold on, where's the program now? Here. The way this is deployed, we do check for pub keys and that is the pub key. But the problem is in this script, you do expect the actual key pair for this pub key. Because yeah, the program has hard-coded that it just allows this as the pub key. Such that only this guy can provide that config, which makes sense. But what does not make sense is why it wasn't created yet. Like, because this doesn't exist, does it? Account doesn't exist. I guess I will need to deploy that myself. Ah, that's annoying. God, that's annoying. But okay. Nanotoken program. Oh, and then probably also we want to change that address then to ours. And also we want to change that address then to ours. And then we build it again. Okay, now we should have a release Nanotoken SO. And I guess we might need some more sol, but I can try if it's like small enough so I can afford it. Solana program deploy. Program ID is NTP and program is in target SBF release Nanotoken SO. Let's see. What could possibly go wrong? Hey, looking good. Nice. I still have 1.4 sol. This is cheap. Even the program is cheap. And check this. It exists on DevNet now. Haha. And check this. I should now be able to initialize this account. Nope, I don't. Shit. We're still calling the gigabit. Where does it have that from? Where do you have that from? Oh, probably you have it from there, but I need to rebuild this because Nanotoken changed. Whoops, Nanotoken changed, so this changes. Hammer time. There we go. And now, no. Custom program error 0x0. System program create account address. We're trying to create this already in use. You don't say. Wait, this is my config or is that the other config? This, what? Wait, no, I did not. Wait, no, why? No, this is so bad. This is so bad. Oh no, no. See, that's the issue. That's exactly the issue why I said you shouldn't do it this way. Look how stupid that is. Because what they're doing is create config here, send and confirm that transaction. It already sends and confirms that transaction just for creating that account, instead of creating an instruction that we then put into that transaction that creates me all the other accounts. No, we did a separate just system program create account where we assigned it to the other program. That's what happened when I've ran it first without changing the program ID. Oh, damn it. I will need to deploy the program again because, well, no, at least I would need to redeploy the program. I don't need to change it completely, but I will need another config account because I can't get that back. Man. Come on. I need another config. There. This is my new config now. Forget about the old one. We can throw that away. This is my config now. And Constance, we need to change this. And then we will need to rebuild the program, redeploy the program, then not forget to rebuild this thing with the new config address, and only then we actually run this thing. Oh man, what do we get? Still a 0x0. Create account address. The mint already in use. Oh, did that same thing happen for the mint? Yeah, the same thing happened for the mint. Man, put that in one transaction, not in two. Come on. I mean, I could rewrite it to do that, but I'm also lazy, so I'm just complaining instead of fixing it. But anyway, that should be easier to fix. I'll just create myself a new mint. Mint. Forget about that. This now my mint. But the problem is now it's again not gonna work because now the first one is just failing because I created the config account already. Yeah, now it's probably gonna kill me for the config account. But hey, at least this one is now owned by my program. So what I'm gonna do is simply not send this one. This is so bad. Why do you use this? This is so bad. Anyway, rebuild, run, again still in use. What? What are we talking about now? Oh, I forgot to save. That's why the building was so quick. Classic. There we go, but now. So now you can create the mint. Here we go. And initialize. Looking good, eh? Great. So made that work. That was a freaking mess, but whatever. We have the config account. We could even look at that, because why not? We see that we have data on this account, and the data is 1 for the type of account is a config account, and then here what's in this config account, the next mint is 1. Oh, because I already initialized a mint, so index 0 is already taken. That's why it was already increased to 1. Oh, that's cool, because we did initialize a mint. Let's check the mint. What else did I do? Probably this one is the interesting transaction where we did all of the things. Yeah, we call this program with all of that instruction data, and we could now analyze what all of that does. So 2 is probably an initialize account, initialize mint. Anyway, but we did several things all in one instruction, mint. Or maybe it was just the mint, I'm not sure. But we definitely called a mint, and that was my mint. There are 2 instructions on that as well. This one was init mint. So init mint was called first with index 1 seems to be init mint with the authority, and that's the mint index, right? I think. I could read source code again. All zeros for the 0th mint. Weird, but that's how it goes. That's it, right? That's how that works. No, decimals. Did I create a 0 decimal token? It's weird that decimals is a U64 as well, but yeah. Maybe I created it with 0 decimals. That's also fine. Whatever, I have a 0 decimal token then. Is that true? Did we do a 0 decimal token? Yeah, look at this, 0 decimals. Okay, sure. Good, I mean, I'm at 2 hours. I should get stuff going. That's not the interesting part, right? This, I mean, yes, even that uses low amounts of compute, but also it uses accounts that need to be in all of those instructions, so that's not ideal. But the interesting part is transfers. So let's do a transfer. Single. Attempt to debit an account with no record of a prior credit. What are we trying to do? We get the token accounts with the mint 0 and the chuds. And then who is signing? Signing is the chud 1 is signing. Okay. I don't know why we need an instruction to a no program, but whatever. Okay, fair enough. What's your address, chud 1? Cool. 0.1 sol you shall get. Oh wait, first is this. Always get that wrong. Is unfunded. Yes, freaking funded. That's the whole point of this instruction, man. Okay, done. Try again. Whoa, transaction exceeded max loaded accounts data size cap. Max loaded accounts data size exceeded. Now that's interesting. Max loaded accounts data size exceeded. Never seen that before. It's not like I'm loading a lot of accounts. Let's see what we have in this transaction. So, signature, account keys are just those. My chud 1, the 2 accounts that are sent from and to, compute budget, the program I'm calling, there's a block hash. My data is also not too big. It's one transfer instruction with one token that I want to transfer. It's simple. Transaction exceeded max loaded accounts data size cap. Do I get that error from the program? No, because then I would get some logs. I get no logs. Transaction exceeded max loaded accounts data size cap. So one of the accounts data size might be too big, but that doesn't what? Let's check those accounts. This is weird. Like it's not really 56 bytes. Another 56 bytes as expected. This should be a 0 byte account. 0 bytes. Compute budget should be, it's a native program, damn it. And this guy, legit is a program, that's it. What the? I guess we're learning something about Solana. You gotta work with random programs to, you know. But what is happening here? For real, I don't get it. Let's just simulate. That's all it gives me. It just says max loaded account data size exceeded. No instructions, no logs, no return data. But what's wrong with my transaction? What is this? Where does that happen? We're moving far away from nanotokens, but that's okay. So where do you live? Where are you thrown? Accumulate and check loaded account size. Requested loaded account size. But what's the requested? Get requested loaded accounts data size limit from the transaction and the feature set. Compute budget limits. Loaded account bytes. Okay, it has something to do with the compute budget program. Wait, what am I doing with the compute budget program here, actually? Because I'm doing something with the compute budget program as well. I'm requesting CUs though. And then set loaded accounts data size limit. There, it's right there. That's the amount of bytes. Interesting. I think that's new. And it looks like I'm not requesting enough. I don't know how much I need to request. I'm gonna just double this for now and see if that makes stuff better. I just want to get it to work. I mean, they do it for a reason. They want to be lean as possible. But I want to get it to work for now. Yeah, look, that was it. That was the problem. We didn't request enough. Hey, we're learning stuff. That's how we learn, right? You fail and then you try and fix and then you learned. There we go. Now we can simulate it. Wonderful. I have never seen this before though. And we used 548 compute units. We requested 600. That's pretty decent. 600 compute units is not a lot. For a transfer, I mean, pretty nice. Do you want to explain to me why the account is not enough? I mean, I can't explain those bytes. If I would calculate that, how would I do that? We check the instruction. We have 1, 2, 3, 4, 5 accounts. And they have, how many bytes is the metadata for an account? I don't know. But they all don't have that many. 64 kilobytes. Why 64 kilobytes? You know, I'm just gonna leave it like that. And I'm gonna put on my list, this could be a topic for a separate video one day. For now, I'll just say, good enough. Or maybe I don't even need to do it times 2. Maybe it's just Maybe we just need 96 times that, or even just 65. I could find the right number. Maybe we were just off by 1. Nope, we were off by more. Because I don't know what that size really is. That's again enough. Cool. All right, well then let's get back to actually doing this. Let's get back to not just simulating, but actually sending it. Let's actually send tokens finally. Boom. Let's go. Give me a transaction. I would have expected you to give me a transaction signature in return, but I'm just gonna assume that it worked. No. Oh, there we go. We got an error. Invalid type. So for some reason it still doesn't like it, even though we can simulate it, but we're still getting errors on actually sending it. No, we get the error on wait, don't care about that transaction stuff. Was there something sent from me? Oh wait, no, we're not sending from here. We're not sending from that account. We're sending from the chat. Anyway, let's try again. Yeah, we are getting a signature. Just this conversion here. For whatever reason you want it as binary. Nah, give it. No. I'm happy with a normal signature. Thank you. So it actually does work. Wonderful. And we see compute. But yeah, so those are the interesting things. We have an unknown instruction to the compute budget program. So 69K, yeah, that could be it. And 4 is the instruction for requesting account space or whatever. And this stuff is so new that it's an unknown instruction to the Explorer. Wonderful. Anyway, the interesting part for us is this, where we do a transfer of 1 token. And the program itself used 248 of 300 compute units. Nice. And 300 of the compute units we just used for the compute budget program. But that's pretty cool. That's pretty lean. That's a very small transaction in total, you know, with its 548 compute units. And we can do a transfer with it. That's pretty cool. Let me check the accounts now. I think that's the recipient. Because obviously, the Nanotoken program is not integrated in Explorer yet. We will need to manually check that account. Solana account, this one, and then manually decode what's written here. So number 3, it is a token account. Then this is the authority, I guess. And then don't ask me what this is. Let's look it up quickly. Token account. So owner, discriminator, owner, that's that. And then mint. Oh yeah, the mint. Mint number 0. Mint number 0 and balance is 3. We have 3 tokens in there. And if we send one more, there we go, and query that account again, then we have 4 tokens in there. Nice. And the other token account, this one, should have the remaining. How many did we mint? I don't even know. This one has, oh, still quite a few. How many did we mint? Probably a million or so. So that's the remaining 999,996 tokens, right? There we go. Oh, even 999,999,996. Told you. Cool. Yeah. So that's nanotokens. We can transfer nanotokens. We could also now hammer some. Let's see how that would look. Hammer. I'm not sure if that even works, but we'll just pump out some just to see. Oh, 1,000 transactions sent. Where are all the transactions? I don't even see all of the transactions that supposedly sent. It's a scam. Hammer time! 600 TPS. I think this thing is messing with me. It's pretending to send transactions when it doesn't actually send transactions. Because if we look here, I don't see anything here. I don't see anything on chain. I don't know what you are, if you're just simulating or actually sending. It does a try send transaction. And that was the old way to do it. Let's do it that way. Maybe that works. Yeah. Now we're at 30 TPS. We sent 190 transactions, but did those actually land? Do we actually see some transaction on chain now? No, still not. So something is not working with that hammer, but that's all right. It looks to me like we are not sending any transactions. Yeah, the hammer thing is not working. And I can't be bothered to get it to work. It's also not that important. The important thing, or the interesting thing, let's send another single. We send another single. We check the account. Now we have 5 tokens. And we should also see a transaction here. Yes, we do. We see that for less than 600 compute units, we can send a token with this Nanotoken program. And we can send 2 tokens in one transaction. Should we also do that? Maybe let's do that by myself, just as an exercise. Instead of single, I do double transfer. And then I'm gonna borrow the code for the single and do the double. So basically what we will need to do now... Oh, wait, hold on. I can just change the number of transfers to 2. I mean, it's implemented that nicely anyway. And then it takes that times that, and then for as many number of transfers. Hold on, does that also do that? With the accounts is a vector. I think I need to add the accounts one more time. I don't think that works like this. Let's try it anyway. Let's see if I can just call double. Transaction simulation failed. Computational budget exceeded. As one would expect, if I do more instructions, I need more CU. Okay, that's fine. So for the double, we gotta request a bit more. Let's say, well, just to be safe, let's do 900. That's for sure enough. Let's try. Success, success, success. Invalid program argument. Config does not have expected pub key. I mean, invalid program argument I get, but why it says config doesn't have expected pub key, I don't know. Because we don't put in the config. Oh, but wait, it thinks we do another instruction, I think. So we do number of transfers 2. So the instruction data is number of transfers times the transfer arcs. Yes, but then I have all zeros at the end, and I will still need to change that. So instruction data 0 to 8. And we will need to loop this. Hold on. We will need to say for I in 0 to number of transfers. Gotta do this. No, this. Actually, with this. But first, let's just do the instruction data, and the accounts we do later. So instruction data... One instruction length is this. I'm gonna get this out. And then we say instruction length to instruction length plus 8. Actually, let's make an offset. Then we can use this offset. And then here as well, we don't say 8, we say offset plus 8 to offset plus 8 plus the size. But then we should have the instruction data, just to prove that I understand what's going on here. Let's build this. Now the instruction data should be correct. The accounts are still missing, but let's let it fail. Let's let it fail, and it fails with insufficient account keys for instruction, as expected. Because we also need to add the accounts again. So for every time where we do a transfer, in this case it's just 2, but for every time we need to say from which account to which account and who the signer is for those bulk transfers within one instruction of the program. So we just extend it every time as well and build that again. And now I would say it should work, a double transfer. Check the account one more time. We have 5 tokens. We do a double transfer. Transaction goes through. And we have 7 tokens. Isn't that nice? And you can check that transaction. We see it's just one instruction, and it just has, it's even aligned pretty, you know, twice the same, twice the transfer with 1 token, and the accounts are double. But it's not like we need to put the pub keys in there twice in the transaction. It's just the indices, so it's just the 3 bytes. It's not like that blows up the transaction if we have the same accounts several times. So if you're worried about that, that's not the case. And the total is now 413 for those 2 transfers, which gives us a total of 700 compute units. And we can scale that up, right? I can do, I don't know, 16 transfers in one. I think that should also still work before we hit some limits. Let's see. Nope. Oh yeah, we need to request more compute again. You know what? I'm just gonna request, I don't know. It doesn't matter. I do 10K. We will see how much it actually takes anyway. Could adjust that later. And even 16 at once, no problem. I now have 17. No, 1, 7. That's the 16 and the 7 we had before. Nice. And also that transaction is just one instruction that we call, just with always the same accounts and a bunch of times always the same instruction data. And that cost us 2700 compute. As compared to the token program, if we do a transfer there, that takes much more compute. Just to compare real quick, let's just real quick do a SBL token, create a token, create account for this token, mint this token, create account for another owner, fee payer is still me, and then transfer this token. And this transfer of one token with the regular token program costs 6,000 compute units. Why is that so expensive? Well, because the token program just does a lot more things. You know, a single transfer checked requires 6,000 compute units. With 6,000 compute units, we can do, let's see how many we can do. Let's see if 64 still works. That would be fun. Nope. Now our transaction is too large because you always need to encode the transaction data. Well, then let's just do 32. Insufficient account keys for instruction. Array vec is full. How much fits in this array vec? I can't put that many accounts in the array vector. 16 and 8 is 24. Let's try 24. Will that do? No. Fine. Let's stay with 16 then. So yeah, with 6K compute units, I can easily transfer another 16. There you go. 27 tokens, even within the same instruction. And that just cost me half of what a transaction with a token program would cost me to send a single token. So the Nanotoken standard is definitely more CU efficient. Is it better? Meh. It has less functionality, of course, less audited and less, battle proven, but it's a nice step in one direction of if you need really efficient tokens, maybe you want to build on that, or maybe you want to use it, see or get inspired by it, right? It's certainly a very efficient implementation and it's cool to have a look at it. Yes, we are the cool kids looking at the efficient implementations. Haha. Anyway, I think I'm gonna leave you. Yeah, I think that's good enough for today. Hope you learned something, even if it's just that we can request the amount of storage that we load from accounts with a compute budget program. That's a new feature apparently. But yeah, Nanotokens, pretty efficient in the transfer, somewhat questionable with the mint and the using an index as the mint. I don't like that particularly. But yeah, I guess this is just a proof of concept that you can create a token that can be transferred super effectively or efficiently with really low CU usage. And that can be really helpful for some use cases. Most things will be okay with the regular token program, but if the regular token program was a bit more efficient, then, we would have more block space. Or we would be able to fill block space more efficiently. However, I'm not saying that the token programs are bad. Given the functionality they have, they're okay. Just specific use cases might want to use a more efficient standard. And this is a good first draft for a more efficient standard. I'm not saying we should use this. I'm saying we could get inspired by it and build a more CU efficient token. Because we already have 2 token programs. We can have several that are made for specific use cases. And I would now like to say we should just let it implement the transferable interface, but that thing does not implement that interface because it tries to be, lean and have several transfers possible in one. But yeah, you could on top build that interface if you needed that. Just makes it less efficient again. But yeah, it's always trade-offs. As with everything, like the length of YouTube videos, and I make the trade-off that we go into details and therefore have long YouTube videos. Been sitting here for 3 hours. but good enough. We did get an impression of the Nanotoken program. We did deploy it ourselves. We had a look at it. It's pretty cool. Several things that we can improve on. But yeah, overall, quite an interesting program. I like it. Fairly easy to understand. And it is pretty efficient with the transfers. I mean, you get a transfer for 2 system program instructions. And they are really low with the 150 compute units. So yeah, that's pretty cool. Anyway, I'll see you in the next video. Like this one if you enjoyed it. Make sure you are subscribed in case my Twitter gets blocked or whatever. Watch other videos. And I will see you at Breakpoint, where the Fire Dancer team might be talking about the Nanotoken standard. Not that I know, but it could be. See you there.